In this lecture, we are going to introduce a very important tool in topology, the degree of a map between differentiable manifolds. It is essentially the number of times that through the map, the domain wraps around the target space. In this way, we are entering into the domain of algebraic topology. And in order to study the degree of a map and its properties, we're going to exploit the results that we already introduced in this course, as for instance, properties of the space of differentiable maps or transversality. We're going to study the degree of a map F between compact-oriented manifolds without boundary of the same dimension, and where the target manifold N is connected. Okay, intuitively, this degree is the number of times that M wraps around N, counted in an algebraic way, because it can be, for instance, negative. And we are going to see in the next lectures that it is a homotopy invariant, which makes it interesting because we can use the degree, for instance, to determine sometimes whether two maps are not homotopic, and also allows to calculate in a simpler way many times the degree of a map, because we just have to find a simpler map in its homotopy class and calculating the degree for the latter map. Consider now a compact manifold with boundary. We already know that the algebraic normal bundle of the boundary is orientable and indeed trivial because it is a one-dimensional vector bundle. This is essentially the reason that provides the colors, okay? And we know too that there exists an orientation by inward normal vectors. At every point, what we need to give is an oriented base of the space, if this is the point X, of the space of this Gaussian space. And essentially, an oriented base is going to consist of just one element of this space, and it's going to be the class of a tangent vector u to M that points towards the interior, okay? And this gives a coherent orientation for the algebraic normal bundle. Now consider a compact manifold M with boundary. As we said, there is an orientation of the algebraic normal bundle of the boundary by inward normal vectors, and we have this short exact sequence. If we assume that we have an orientation omega of M, then the tangent space of M is oriented, as this vector bundle is oriented, and its restriction to the boundary of M is also going to be an oriented vector bundle. We have the algebraic normal bundle that is also oriented, and so orientations in the two last vector bundles of the short exact sequence provide an orientation of the tangent space of the boundary. And we have fixed omega, the orientation of nu by inward normal vectors, that's going to induce an orientation partial omega of the boundary of M, right? Indeed, if B is a base of the tangent space of the boundary at the point X, then the orientation associated to B is equal to partial omega if the base consisting of B and U has orientation omega, where U is indeed an inward normal vector. It's a tangent vector of M at X that is normal to the boundary and inward. Even if we work with differentiable maps between manifolds without boundary, we need to introduce manifolds with boundary to understand the properties of the degree. And so we are going to work sometimes with manifolds of the form M times the closed interval. because these are natural domains for homotopies. And if we fix an orientation theta of M, we are going to consider an orientation omega, which is just the product of theta and omega 1. Omega 1 is the standard orientation of the line. What does it mean, this product? Okay, in order to define this orientation omega, we have to provide, first of all, we have to consider here the class of base of the tangent space at some point xt of M times the closed interval. Okay, this is the orientation at the point xt. Let's recall that the tangent space of this product, okay, at the point xt is just the product of the tangent spaces, is the tangent space of M at x times tangent space of the closed interval at t, but that's the same as the tangent space to the line at t. Okay, indeed it is the line. And what we are going to do now is provide the base that is going to define the orientation omega. So omega of xt is going to be the class of B0, and here we're going to consider 0, 1. The first component is in M and the second component is in the closed interval, such that, of course, we have to say something more, such that B is an oriented base of M and provides the orientation theta, such that the class of beta is equal to theta, to theta. And so that's, by definition, this is the definition of the orientation omega at any point, okay? So consider now an orientation theta of M and the product orientation in M times the closed interval, the product of theta and omega 1, which is the standard orientation of the line. Assume that M is a manifold without boundary, but even so, M times the closed interval is a manifold with boundary. And indeed, the boundary of M times the closed interval is equal to M times 0 union M times 1. Now, in M times 0 or M times 1, we have two orientations. One of them is the orientation theta, because we can identify any of these sets with M. But the other one is the orientation partial omega induced by omega in the boundary components of our manifold M. And we want to compare those. What happens is that by definition, the orientation partial omega at a point x0 is the orientation of a base B of the tangent space of the boundary at the point x, where the orientation induced by B times 0, and here we have to consider by the definition of the induced orientation of the boundary an inward normal vector. But if we consider the closed interval 0, 1, an inward normal vector at 0 is positive vector. So we have to consider this and this being equal to omega at the point x0. And by the definition actually of the product orientation, that implies that the orientation of the base B is equal to theta. And so we have that the partial of omega at x0 is just theta at x, okay? In the same way, what happens when we consider partial of omega at a point x1 is going to be the orientation of a base b, where now, when we consider b times 0, and now an inward normal vector, but if we have the closed interval 0, 1, an inward normal vector at 1 is a negative vector. So when we have this is the orientation omega. And by our definition of the product orientation, the orientation of B has to be minus theta, okay? Because here we are changing signs, so in order to preserve the orientation omega, here we need to replace theta with minus theta. And as a consequence, we get that the orientation partial omega at a point x1 is minus theta x. So we get these two equalities over here. Okay, as a consequence of that, that the orientation induced by omega in both boundary components is indeed different and indeed opposite, we write this property in this way. The boundary of m times 0, 1 is going to be m times 0. Here it should be an union, okay? Union minus m times 1. And this minus m actually reflects the fact that these two copies of m are oriented in opposite ways. So we talked a little bit about orientations. Now we are going to try to define the degree of a map little by little, introducing new properties that are going to allow at the end to define this degree and show that it is a homotopy invariant. So consider m omega and n theta oriented compact manifolds without boundary of the same dimension and assume that n is connected. Okay. And now let x be a regular point. A regular point is a point in which the differential of f at x is surjective by definition. But since m and n have the same dimension, a regular point is a point in which the differential is an isomorphism. So we can actually ask whether or not the differential preserves orientation. If the differential of f at x preserves orientation, in other words, sends omega x to theta of fx, then we say that x is of positive type, and we define the degree of f at the point x as equal to 1. If, on the other hand, the differential reverses orientation, we say that x is of negative type, and then we define the degree of f at x as minus 1. So at regular points, the degree is either plus 1 if the differential preserves orientation, and minus 1 if the differential is orientation reversing. Given a regular value, y, okay, we consider all the points in the preimage and we just sum the degrees of f at those points. Let us actually realize that the preimage of y is actually a submanifold of m because it's the preimage of a regular value, and the dimension is equal to 0. Since m is compact, that implies that the preimage of y has finitely many points. And so this sum over here is defined. If there is no point in the preimage, then we say that the sum is 0. So we have a definition here of a degree in which we are fixing a regular value and orientations omega of m and theta of m, okay? Let m and n be oriented compact manifolds with a boundary of the same dimension and assume that n is connected. In this setting, we defined the degree of fy where y is a regular value. Here we are not writing the orientations because they are implicit. Okay, and this is essentially the algebraic number of times that f covers a neighborhood of y. Instead of just looking at the number of preimages of y and counting all of them, we are giving a positive weight, which is equal to 1 indeed, to those points in the preimage in which the map f locally preserves orientation, and we weight with -1 those points in which the map f locally reverses orientation. Now we are going to see an example of the degree of a map. We're going to consider the maps c to the power n, where n is an integer number. These are maps from C star to C star. C is the complex plane, and here we're using complex notation. This map induces, for every n, a map Cn from the circle to the circle, okay? And if n is actually different than 0, then every point in the circle is a regular value. If you actually consider this map in polar coordinates, theta, then this map is just the map that sends theta in n times theta. So when n is different than 0, the derivative is different than 0 at every point. So every point is regular and every value is regular. When n is 0, the derivative is positive. When n is negative, the derivative is negative. So what we get is that if we calculate the degree of c to the n in a point y for n different than 0, if n is positive, then every point in the image has n preimages, and since we are in the orientation preserving case, all of these preimages are of positive type. So the degree is going to be n times 1, in other words, n. What happens when n is negative? In that case, every point has minus n preimages, but all of them are of negative type. So the degree of Cn for the regular value y is minus n times minus 1, in other words, n. So we have this degree being equal to n for every y in S1 and every n an integer number and a non-vanishing integer number. In the case in which n is 0, this map over here is constant. And of course, the unique point in the image of this map is not a regular value, but all the other points are. Okay? So if we consider y in the complement of 1, obviously this point is not in the image of c to the n, so the degree of Cn for that regular value is going to be 0. So essentially, the degree of c to the power n is equal to n. The next result is crucial to show that the degree is a homotopy invariant. Okay, this is actually the result that is going to imply that property. So consider W a compact oriented manifold of dimension n plus 1, and let n be a connected compact oriented manifold without boundary of dimension n. The dimension of W is the dimension of n plus 1. Consider now H as the infinity map from W to n. W is going to be a manifold with boundary, and assume that Y is a regular value for both H and the restriction of H to the boundary of W. Then what we want to show is the degree of the restriction of H to the boundary of W, which is a manifold of dimension n, for the regular value Y is equal to 0. Okay? The first thing that we have to notice is that the preimage of y, since h is actually y, let's recall that y is a regular value for both h and the restriction of h to the boundary of w. And this implies that the preimage of the point y is indeed an ith submanifold. Okay? Of dimension, and the codimension of this net submanifold is indeed going to be equal to n. Since W has dimension n plus 1, the dimension of this net submanifold is equal to 1. Okay, so now we can make a picture here of the boundary of W, and the preimage of Y is going to have several components. Okay, some of them are going to be completely contained in the interior of W, and other components are going to be arc that intersect twice the boundary of W transversally. Okay, we're going to consider one of the components, gamma, that intersect the boundary of W. And now we consider beta and orientation of the tangent space of gamma. For instance, it could be this orientation. In this way, we are going to consider here the initial point A and the final point B. We are going to consider two nu, which is going to be the algebraic normal bundle okay, of gamma in W. And it is interesting because the fiber at the point A or B can be identified with the tangent space of the boundary. Okay. Indeed, we consider the orientation alpha of this algebraic normal bundle such that alpha c direct sum with beta c is equal to gamma to omega c, omega being the orientation of W, okay, for every c in gamma. What we can see is that here the orientation beta is pointing to the interior of omega, and so as a consequence what we have is that alpha A is equal to the orientation partial of omega at the point A, and that here the orientation beta is an orientation that points toward the exterior, and so as a consequence alpha of B is going to be minus partial omega at the point B. Okay, we have alpha A equal to partial omega at A, and alpha B equal to minus partial omega at B. Let's consider now C a point in gamma. For this point, we can consider the differential of H at the point C, which is going to be a map between the tangent space of W at C and the tangent space of N at HC. But of course, we can here divide by the kernel of this map. And the kernel of this map is the tangent space of gamma at C. So it's the normal bundle, okay? And what happens then is that this map is an isomorphism for every C in gamma, okay? This is an important property. Now consider what happens if the degree of the restriction of H to the boundary of W at the point A is equal to 1. that implies, in particular, that the differential at the point H of this map is sending the orientation, the positive orientation of the boundary to the positive orientation of n. Okay, theta is going to be just the orientation of n. But if we consider this setup, this is the same as saying that the differential of h at the point A is sending alpha A in theta of HA. Now, since these are isomorphisms, if this equation holds for A, it holds for every point in gamma, and in particular, it holds for B. So we're going to get that the differential of H at B, and this differential is this map over here, sends alpha B to theta of HB. But now we have to realize that alpha is minus partial of omega. So that's going to imply that the differential of the restriction of H to the boundary at the point B sends partial omega in minus theta of HB. And in particular, that implies that the degree at the point B of the restriction of H to the boundary is equal to -1. So these degrees are opposite. Of course, what happens if this degree is -1? We're going to have a similar analogous property. If this degree is -1, here we have to consider minus, here we have minus, here we have a minus, okay, and here we have a plus, and this degree is +1. So these degrees are opposite. As a consequence, okay, if we are considering the preimage of y, as I said, it's going to have some components. Some of them are circles containing the interior, and some of them are arcs. And what happens when we consider the degree of the restriction of h to the boundary for the value y is that these points in the preimage of y in the boundary of w come in pairs, okay? And in every one of these pairs, in one of those points, the degree is 1, and in the other is -1. So the sum in every pair is 0, so the sum over all points is 0, as we wanted to prove. In our next lecture, we are going to define the degree of a map and then see that it is a homotopy invariant. Indeed, the result that it is behind these properties is the last theorem that we proved in today's lecture. Thank you for your attention.